Now we looked at rotational inertia, which was sort of like the rotational analog of inertia or mass. And we had this formula that said torque equals rotational inertia times acceleration. Force equals mass times acceleration. Think about it that way and you won't forget it. Now we come to something we remember. We had momentum, right? Mass times velocity. I think you can probably already guess where we're going with this. We've got a letter for something called angular momentum, L, angular momentum. Now, if we're going to do a rotational analog, we'd go with the rotational form of mass, which is I, and the rotational form of velocity, which is omega. And we've got ourselves a new formula, which we should know. This is called angular momentum. What are its units going to be? Well, we know that the units for I are kilograms, mass, radius squared, and radians per second. But we don't put the radians in a formula, so it just becomes kg m squared per second, right? Now, that's your angular momentum. This is where we're going to see a few interesting things. Different I's, right? Different I's. I, we found, was dependent on mass distribution. So, if you have more mass a greater radius away, then you have a greater I. If you have a greater I, you're going to have a greater angular momentum for the same omega. These are the things to think about a little bit. We're going to have something called conservation of angular momentum, just like we had conservation of momentum. What does that mean? That means, just like when we had conservation of momentum, we used to say if there was no external force acting, then we could say there was conservation of momentum. If there's no external torque operating in a system, then we can say there will be conservation of angular momentum. Now that's the sort of situation where you've got two objects, right? Now two objects might be, you've got this round object, maybe it's rotating, maybe it's not, maybe it's just sitting there, a disk, and we get another object come along and hit it, right? Now these two objects as a system, we can say there's no external force. This object was just cruising along at a certain velocity and it hit this object. A collision, just like with our conservation of momentum problems. But now we're actually looking at the system and saying, how much angular momentum did it have before? And since there's no external torque, then afterwards it's going to have the same angular momentum. So we can say L before equals L after. And that really helps because we can then figure out things like what's the velocity going to be afterwards. So this little guy here, we could work out its angular momentum, this guy's angular momentum, and then we'd have the total angular momentum before. Afterwards, all right, we'd be able to go, okay, now we can figure out backwards and maybe figure out their angular velocity, because remember L equals I omega. Now that example might seem a little bit confusing because there's another formula for angular velocity which we haven't looked at, and it's this one. L equals mvr. Now that one there is for this type of situation where you've got a point that you're measuring your rotation about, and you've got an object moving with a velocity, so that object's moving with that velocity. We can ask ourselves, what's this mass? It's got a mass, it's got a velocity. What's this mass's angular momentum relative to that point there? And what we would do is we'd say its angular momentum is equal to its mass times its velocity times r, the perpendicular distance between the center of rotation and the mass you're talking about. So to get this one's angular velocity, we just go mv times that distance. Now for that problem we were just looking at before, when we want to know the total angular momentum for the system, if this little guy here is not even rotating, or whatever, if he is rotating, it's all right. We know the I for a disk, so we use two different formulas. We've got that one. If that disk is rotating, then we use I for that disk plus the omega for that disk to get I for the disk. We've then got this stone comes along that was traveling at a certain velocity, and we would have to use this formula. How? L equals mvr to work out its angular momentum. We'd add them together, and then we'd go, okay, that's our total L, and that's going to be the same afterwards. Now if this rock or whatever's landed on there and stuck to it, then afterwards L total is going to be the same. We would then need to work out a new I to figure out the new omega. And the new I would be the old I, because that hasn't changed, plus an I from a mass at that radius squared. So we would have a new I, and that would change the omega. As we do some problems in class, you'll understand that a bit more. But there is another thing we need to know about angular momentum with that sort of formula. This formula here, L equals mvr, notice that little symbol there. It just means perpendicular distance. Alright, now if I have a planet here, for example, and I've got something moving at that velocity in that direction, it's a mass, could be a satellite, that's its velocity. But the center here, it's not perpendicular. That's the distance. And it becomes a vector equation to do this normally. L equals mv. Distance doesn't really work because these actually need to be vectors, the v and the d, and they're not. So we use the perpendicular distance. You just extend the velocity back until you can make a perpendicular distance with it. That one wasn't done too well, was it? So you extend it back till you can make a perpendicular distance, and you use this distance. You don't use that one. It's got to be a perpendicular distance for this formula to work. Which is all very well if you sort of had a planet here and you've got a satellite orbiting and the whole thing is all at 90 degrees, then this is the perpendicular distance, and you just go mass, velocity times that distance, no problem. So that's mvr, angular momentum. Very similar to what we used to do with normal momentum. Remember, no external torques means no change in momentum. So an isolated system, the angular momentum can't change. Now, is there anything else to be got out of this whole thing on angular momentum? We've got our two formulas like that. Does it make sense? I suppose we looked at the units, didn't we? Angular momentum equals I omega, angular momentum equals mvr, perpendicular. That's probably enough.